this part down. But if you remember when we did derivatives, we started off talking about derivatives in a very general sense, slope, tangent lines, right? And we did all the chart stuff before we ever learned any derivative formulas. We did everything graphically. But then when we wanted to talk about the slope at point A, you remember we said, well, we can't do slope at one point, we need 2 points, so we made ourselves a second point, which we called A plus H. This was f of A, right? Remember this? This was f of A plus H. And we said, if you're going to do the slope, you've got to subtract the y's, and you've got to subtract the x's, like so. That would be your slope. And then what do we add to that? What do we add on to that? The limit as h approaches 0, right? In other words, we had to say, okay, we're going to let those 2 points become 1. And so, so after we've looked at it informally, we dug into the technicalities of it, and we used notation to actually describe what was going on, excuse me, with the derivative. So that's where we're going to go today, to get into approximation. We already got this informal idea of antiderivative and how we can find some. But now we're going to really, really get into some notational stuff with areas that's very similar to how we approached it when we did derivatives. Okay? All right. So that document that I sent to you on your calculators, let's open up this one first, the LRAM, RRAM, MRAM calculator. Did you, Brock, were you able to get, to do it again? Did you get logged in? Mark, how about you? Okay. All right. Yeah, 16, just missing a couple. Kelsey, you're just getting logged in. Okay, so anyway, it's going to send you a couple of documents once you guys get logged in. And they're really just to look at, okay? They're just to look at, but it's nice to be able to have it in your hands and be able to look at it. Excuse me. All right. Now, what this stands for, RAM stands for Rectangle Approximation Method. Rectangle Approximation Method. And the L is for left and for right and for midpoint. So we're going to be talking about left rectangles, right rectangles, and midpoint rectangles. Now, what do we mean by left, right, and midpoint? If we scroll over a couple of pages here to page, I think it's 1.6. Okay, here's 1.6. So if you want to scroll there in your document. So what we have here is we have a function. Now we're going to start with simple functions. We said we use approximations when we can't find the exact area with an antiderivative. Well, here's one we could, x squared plus 1. We can do that easily. So we'll start with ones where we know the exact area, but then see how we can approximate it so we can compare it, right? So we start with just a simple parabola here. And I'm going to go from 1 to 3. And I'm going to throw some terminology at you here today. So we're looking at the area from 1 to 3. And so what I've done is divided it up into 4 subintervals. So this is the interval from 1 to 3. That's our interval. We divide it up into subintervals. There'll be 4 of them in this case. How wide is each subinterval? Be a half, right? The whole interval is 2. So 3 minus 1. And then divide by how many subintervals. We'll use n for the number of subintervals. You'll see that a lot. So there's going to be 4 subintervals. Each one is a half wide. Now we want to know the area of each of those rectangles. So we need the width and we need the height, right? Well, how do we get the height? Well, we get the height by plugging into the function, right? Now, in these particular rectangles, you notice in this first one, we took the left edge of the subinterval and we plugged that value into the function, and that gave us the height of the rectangle, right? That'd be f of 1, right? Everybody with me? So notation, we want to get the hang of here today. Everything we do today is about notation. So f of 1 is the height times a half. That would be the area of that rectangle. Now what's this one? What's the height of this one? F of 1.5, and then times a half. And this one is f of 2 times a half. And this one is f of 2.5 times a half. These are called left rectangles, because what we've done is we've taken the left edge of each subinterval and used that number to plug into the function to give us the height, and then we draw straight across and we draw are rectangles. Now, if you go one page over, you'll see, oh, and clearly that's an under approximation, right? Clearly this area is too little, right? Because we're missing this areas here, right? So we go to a right rectangle situation, and those would look like this. Now, what you're going to do in your homework today, and we're going to be doing it in class as well, is you're going to be doing some drawing, right? So those of you with the artistic, like the artistic side of things, you will really enjoy it today, okay? So you're going to get to draw some rectangles. So here, notice what we did is we take our subinterval, but we take the right edge of the subinterval, and we plug that number in to the function to get our height. Okay, those are called right rectangles. And that's clearly too much, right? That's an over approximation. All right, is midpoint rectangles. Okay, notice what happens here. We take our subinterval and we take the midpoint. So what did we say this was 1 to 1.5? So what would that be? 1.25. So this would be f of 1.25. That is the height. And then times our width, which is still a half, right? The width is still a half. Okay? Now those are better, right? Because you got some over, some under, so those are going to give us a better approximation, right? And you might say, well, why don't we always do that? Well, you'll see why, because we're not always going to do 4 subdivisions. We might do 20 or 30 or 40 or whatever. Now, we're going to have to draw those by hand? No. Okay? On our next quiz, the rule is going to be this. If it's less than 10, we'll do it by hand. Okay? If it's 10 or more, I'm going to give you a calculator program that's going to calculate that for you. Okay? All right. So today's homework is going to be all about drawing, though, so we'll be doing it by hand. All right, let's open up the other document I sent you. Riemann sums. I think if you go under the AP Calc Period 3 folder is where that is. Okay, this one's called Riemann sums. And this one's very much the same thing, but it lets us do something a little bit different. I'm going to get downgraded. I didn't update my goal over there. Oh, that's what he was looking for. I guarantee you. How would he know that's not what we're doing? You're right. He might not know that's not what we're doing. That's your just tell that's what we're doing. That's exactly right. All right. Okay. So anyway, so this is very similar. Okay, we got our parabola function here. You can see 4 left rectangles. The difference in this document is you can do some things with it. Like, for example, I can go over here and grab this little dot here, and I can drag it over to M, and now it gives me 4 midpoint rectangles. Or I can drag it over again to R, and it'll give me 4 right rectangles. Or I can drag it over to the T, and it actually gives me trapezoids. And trapezoids are really nice, too. Now, they're more complicated to calculate than rectangles. So that is a little bit of a problem, but we'll deal with all of them. Okay, you can see the approximation to the area, you can see the exact area, so you can kind of compare. And trapezoids do a pretty good job. Okay, and actually the midpoint rectangles did a pretty good job too. The midpoint rectangles were pretty close. Okay, but here's the thing. Here's why in the end it's really not going to matter which one of those we do, because I'm going to grab this slider over here, and we can grab this thing, and we can change how many subdivisions. Well, left rectangles are an under approximation, but if you have enough of them, if you have 100, you get a pretty good approximation, right? Yeah, it is kind of cool how that looks. And so you can really visualize what's going on there. Okay, so that's why I like this. And you can just play with it a little bit, but it just gives you a nice visualization of what we're talking about. Now, compare that to what we did with derivative. And we said we had 2 points. We want the slope at 1 point. So we let the 2 points get closer and closer. We did a limit as h goes to 0. You see a limit happening here? We want the exact area. You can't get the exact area with rectangles unless you have how many? An infinite number. So you can see a limit coming. The limit as n goes to infinity, right? In other words, if we take these left rectangles and we keep adding more and more and more and more, eventually we could get to the exact area, right? I mean, the limit would be the exact area. We'd be getting closer and closer and closer and closer to the exact area if we could do an infinite number of rectangles. Okay, so that's what we're developing. That's what we're working on developing. Now, The big thing is a notation. So the next couple days, the next 3 or 4 days really is all about notation and understanding the notation. So I'm not trying to give you busy work as you do these things. I'm going to be talking to you a lot about writing out your work, showing this stuff, but there's a reason I'm having you write it out. It's all about seeing patterns. And without writing it out, it's really hard to see the pattern. Okay? And so that's what we're going to be getting into here today. All right, I've got one other drawing for you here, just another version of it you can see. Because if your function is going up and down, then you get a variety. Like, for example, here, the left rectangles are over approximation. But then here, when the graph starts going up, the left rectangle is actually an under approximation. You know, so these two are over and these two are under, right? So depending on the function going up or down and so forth, it depends on whether you're going to get an over and under approximation. So those would be lefts, and then we could look at some rights, right? And we could look at some midpoint ones, right? And we could look at some trapezoids. Well, actually, interestingly enough, for a given number of subdivisions, midpoints are actually better than trapezoids. And we're actually, in chapter 6, we're going to show why that is. But they both are good because they're kind of like averages. You know, they've got some over, some under, kind of thing. And so, all right? But the problem with those two is that their formulas are harder. In other words, the problem with the midpoint is you have to do your subinterval, and then you have to take half in there to figure out what we call that the sampling point. The left edge is easy to find, the right edge is easy to find, but the midpoint's a little harder to find. It's not hard to find, but it's just a little harder than finding the left and the right. And trapezoid is just a more complicated formula. You know, rectangles are just length times width, or base times height. So they all have some advantage. And the bottom line is going to be, if we have an infinite number of them, it doesn't matter what we use. If you have an infinite number of them, they're all going to be good, right? They're all going to be good. All right, so we'll move on from there. So here's what we're going to do. We're going to jump right into some homework type stuff. This is not on your homework, but you're going to do one just like this. So we're going to spend some time. Your homework is basically 9 problems. Of the 9, one of them is like this one. I think you have to do number 16. We're going to do number 17. You're going to do number 16. We're going to do number 17 here together. And on number 16, you have to draw 4 pictures. On the other 8 problems, I think you have to draw 6 pictures. 6 of them you have to draw pictures. And I think there's 2 you don't. So you're going to end up with about 10 pictures in your homework problem. Okay? So here's what we have. We have this integral. Because really all I want to accomplish today is for you to be able to write I want you to be able to write these approximations out, these area approximations, and I want you to be able to draw these rectangles. Those are the 2 things we need to be able to do. All right. So we're looking at the integral from -2 to 2 of x cubed. Now, I could have picked something different, but we know this area is what? The red area. Well, it's just 0, right? It's because it's symmetry. It's -2 to 2. This negative is going to cancel that positive. It's 0. The answer is going to be 0. Now, the directions on your homework say this for number 17, and you're going to do number 16, so it's going to be similar. Draw a sketch that illustrates the approximations L4, R4, M4, T4. I'll tell you what that means in a minute. Then compute each, so you're supposed to draw a sketch. Then compute each approximation and compare it with the exact value of the integral computed using the fundamental theorem. So, first thing let's do is let's go over here and let's compute it. And I heard, Kelsey, you were saying 1/4 x to the 4th, which is right. That we would do our antiderivative. Okay, so let's put that over here. So 1/4 x to the 4th from -2 to 2. Put in a 2, we get 16 times the 4th is 4. Minus, put in -2, you get 16 times the 4th. 4 minus 4, sure enough, you get 0. So we know we know that area is 0. All right. Now what they want us to do is they want us to draw an L4. Now you're gonna draw this graph 4 times, right? So when I come around looking at homework tomorrow, I'm looking for these pictures, right? For sure. So they want us to draw and to write out, compute an L4 sum. What that means is left rectangles, 4 of them. 4 left rectangles. All right, now earlier you guys were telling me we were talking about the width, right? And in general, this is our formula for width. Delta x is what we're going to use for our width because that stands for change in x. If you think about rise over run, dy over dx, delta y over delta x is the run, that's change in x. So that's what we're going to call our width, is delta x. And that is b minus a divided by n. In other words, it's your total width, right? In our case here it would be 4, right? 2 minus negative 2. So in this problem it would be 2 minus negative 2. And then divided by how many subdivisions, which is this number right here, 4. So what do we get? We get 4 divided by 4, which is 1. So our subdivisions are 1 y, right? And that makes sense, right? Total width of 4. So it's not like this is that important of a formula, but just it's a total width divided by number of subdivisions. All right, now, so I'm gonna put dots here. I like doing this. You don't have to. But I'm going to put dots here every 1 unit so I really can see my subintervals. Now notice it takes 5 dots to do 4 subintervals, right? Because you got the left edge, you got the far edge, and you got the ones in between. So 1, 2, 3, 4 subintervals are made by 5 points. And I only show that because we're going to write a definition here later, and it's going to talk about n subintervals made by n plus 1 points. There's always one more point there than there is subintervals, okay? That's the only reason I say that. All right, so here's what I want you to do. First, we're going to draw the picture. So we're going to draw 4 left rectangles. Well, how do you do that? Well, you start at your left edge. You go down, in this case, to the function. Sometimes you go up, depends where the function is. You go across one width, and you come back, and there is your left rectangle for that. Does that make sense? We've got to draw a left rectangle, a left edge rectangle. And so we've got to look at our subinterval. We've got to take the left edge of our subinterval and go to the function, and that's our height. So we go straight across. That's our rectangle. So now let's do the next one. So the next one, next subinterval, we go to our left edge, go to the curve, go across one. There's our rectangle. Go to the next subinterval. Ooh, what's going to happen here? We'll just draw straight across. But yeah, there's not going to be a rectangle because it's got no height. The left edge, the function value is 0. That's the height of your rectangle. So what we have is a rectangle with no height, so it's going to have no area. All right, and the last one, at 1, this last subinterval, the left edge is at 1. So we go up to the curve, we go across, and there we go. So now we want to add up the area of those 4 rectangles. Now I know for most of you, all of you, you could just sit here and you could look and you could just calculate those. But we are going to write this out. First question on the quiz next week is going to be similar to this. Here's a function, here's an integral, draw 4 left rectangles or whatever, and compute the sum. And you have to have the sum written out, you have to have the picture drawn, so forth. Okay? Now, here's how I want you to write this. When we write it out, I want to see 4 areas there. 4 rectangle areas. I want to see height times width. So we're going to use function notation. So we're going to pretend this is the f function right here. Or did they? I don't even think they gave it a name. Okay? Yeah, they didn't call it anything. So we're going to call that little f. So what is this? What would be in function notation this first function height? This first rectangle height would be what? F of negative 2, right? Times, what's my delta x? What's my width? 1. Now you say, why do you have to write times 1? I want you to write times 1. I want you to, when you look at this, I want you to see height times width, which is area. Height times width. Okay? Again, there's a reason for it. Not because I'm giving you busy work, because we're going to see patterns. It's kind of like when you were in 4th grade and they were 3rd grade doing your multiplication tables and you had to develop number sense. They made you do them over and over and over and over again until you kind of memorize them. That's kind of what's going on here. we're going to develop a sense of what these things are. It's going to make what we have to do the next couple days easy. All right, what's the next function? Height. F negative 1 times 1 plus f of 0 times 1 plus f of 1 times 1. Now, when you look at that, right away you can see 4 distinct rectangles. Height times width, height times width, height times width, height times width. So this is clearly an area, and so negative 2 cubed is negative 8. Excuse me. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. And we get an answer of negative 8. So those blue areas added together would be negative 8. Of course, we can see that. Those would cancel those. That's negative 8. I get that. But I want to see this right now. Okay? Now, that's a horrible approximation because the area we know is 0. But you don't expect to get a good approximation with only 4 subdivisions. Right? 100? Yeah. But 4, not so much. Okay, next page. Okay? Same thing, right? Draw a quick sketch of it. We're going to do rights, we're going to do midpoints, we're going to do trapezoid. That seems kind of silly, spend all this time drawing things, but actually, they can be a little trickier than you think. Okay? They can be a little trickier than you think. So, I'll give you a little time to get your X cube drawn in there, whatever, but doesn't have to be masterful. Now, I think on the quiz, when it comes time to do this, you want to work at it carefully. I may let you have calculators. It depends on what function I want to give you. Maybe I'll give you the graph of the function, or maybe I'll just give you the equation and let you use your calculators to graph it. Or maybe it'll be such a simple function like this one that you can just do it without a calculator. Okay? Now we're going to do 4 right rectangles. R4. Okay? So I'm going to put my dots on here at my, because I'm still going to be a width of 1. I'm still doing, right? My subintervals are still 1 wide. Still have 4 subintervals, but the difference is now I'm drawing right rectangles. So where will I draw my first one? I'll go to my first subinterval, the right edge, and I'll go down. Now these are called sampling points. I think I said that earlier. What we're saying is in this subinterval, we need to pick a point to plug into the function to give us the height of our rectangle. Well, earlier we did the left edge of the interval as our sampling point. Now we're doing the right edge of our interval. So I plug in that, and there's my first rectangle. Go to my next subinterval, go to the right edge, plug that into the function. Well, that's going to be 0. Go to the next subinterval, go to the right edge, plug that into the function. That's going to be my height. And then last subinterval, go to the right edge at 2, plug that in. That's going to be my rectangle. So again, this is another, I mean, you can tell it's going to be 8, right? I mean, we can see that. I understand. But let's write it down. Now, you want to get to the point where you can write down these sums without even having the picture. As we go forward, we'll do less and less of drawing of the pictures and just writing the sums. Right now, drawing the pictures helps you to write the sum, but in short order, you're going to be able to write these sums without the picture, but at least maybe you'll be able to visualize the picture, and that's going to help. All right, so what's my first height? F of -1 times 1 plus f of 0 times 1 plus f of 1 times 1 plus f of 2 times 1. Now you notice the difference between the left and the right. On the left one, we started at our left edge of -2 and we stopped short of the right edge. And on a right rectangle, we skip the left edge and we're over here and we go all the way to the right. But the idea is we got 4 rectangles there. All right, so we got -1 area. The next one is 0. Next one is 1. Last one is 8. For a final answer of 8, which again is a lousy approximation. That's not what we're worried about right now. Okay, we're just worried about the mechanics and we're worried about the notation of these problems. Okay, hang in there now. We just got a couple more to do. So we're going to do our midpoint now. Now, like we were talking earlier, midpoint trapezoids bring in a little bit interesting scenarios. Kind of had mine done ahead of time, so I got a little advantage over you guys having to draw all this stuff. So slow down a little bit here. But you got those 4 subintervals. The width is still 1, even though we're doing midpoint. That doesn't change. What's my first midpoint? Right there, negative 1.5. So we go down to the curve, and then we draw both directions for our rectangle height. Does that make sense? Okay, it's like that. So we go to our midpoint, negative 1.5, and we go down to the curve, and then right there we draw across, and that's our rectangle. And then we go to negative 0.5, and we go to the curve, and we draw across. And then we go to positive 0.5, and we go to the curve. And so we're getting these little tiny rectangles here. And then we go to 1.5, and we go up to the curve, and we draw across. Yeah, now this one you can tell that now we actually get the exact answer, which is really good. But again, just because of symmetry, because of this graph is symmetrical and stuff. So normally it wouldn't be as good, or those other ones wouldn't necessarily be that bad. But so now it's what? F of, what do we say, negative 1.5 times 1. That doesn't change. The width doesn't change. And then F of negative 0.5 times 1. And it, I do understand it gets kind of redundant doing these things, but it's, you know, hopefully in a good way as you do them. And I just can't really, well, maybe the best way to explain it is to show you in our sample 2, you don't have to get this out, but our sample 2 packet, one of those problems we skipped, this is what we're going to be working on over the next couple days. This problem right here. Okay? See that limit as n goes to infinity, right? We were just talking about that. And you see there's this kind of this pattern of the sequence of stuff, and being able to see that pattern and put it into a function, to fit it to a function and fit it to an integral is what we're going to be doing. Okay? That's the connection. So the more we write these out, we kind of get a sense of patterns. And that's what we're going to need. All right. So there's that. Now you got to do a little more work here. So negative 1.5, we got to cube it. Well, here's what I would say. I don't know if we'll get calculators or not, but fractions will probably be more useful to us in finding patterns than decimals. So what I would do is I would have, if I was doing this, I would have written negative 3 halves here. Now, cubing that is easier now, right? That's negative 27 eighths, right? Cubing that's much easier than the decimal. So I would write that as negative 27 eighths. And then negative 1/2 cubed would be negative 1/8. And then that's positive 1/8. And then that's positive 27 eighths. And that is 0. Okay? But so that'll be my advice. If it's a no calculator situation, use fractions, and then those are easier to work with. All right. But there could be somewhere we use calculators for part. All right, one last one is our trapezoid. Okay, so I'll let you catch up here on this. Just, don't make it fancy. Just draw your x cubed in there. Trapezoids. Now, trapezoids get a little interesting. Number one, they're very accurate, kind of like midpoints, but they're messier to work with, right? That's one of the dilemmas. Because they're not just base times height, right? It's 1/2 the sum of the parallel bases times the height, which would be our delta x, right, for us. So So how do we draw a trapezoid? Well, we start, now let me put my dots in again. Right? One, right? Five dots, 4 subintervals. So how do you draw a trapezoid? Well, you go down on your curve all the way down to there, and then you go to the other edge and you go to the curve with it too, and then you connect those with a straight line, like that. And then that is your trapezoid. Right? That's how you do a trapezoid. So you go both edges of the subinterval to the curve and then connect with a straight edge. Now what happens on the second trapezoid? It's not a trapezoid. I don't know. I don't know if the formal definition, if we could consider that a trapezoid. Because one of the bases is 0. But look at the trapezoid formula. What happens if one of the bases is 0? It's just 1/2 base times height, which is triangle, right? So I think what you could say is a triangle is really kind of a special case of a trapezoid. It can be thought of as a special case of trapezoid. So when you draw this one, you're just going to draw from there to there. And when you draw your second one over, or this one over here, it's the same thing. So they are trapezoids. We're going to call those trapezoids even though they're technically triangles. But, right? And then this last one, again, we would connect from there to there. Like so, and there's your trapezoid. All right, so let's write that out. So this would be 1/2, and now in parentheses, what's my first base? F of -2 plus F of -1. And then what's my delta x, my height? That's 1 again, right? So that's one trapezoid, plus 1/2, and then you can see the pattern probably, F of, we use -1 twice, don't we? -1 is the right edge of this trapezoid, and it's the left edge of that trapezoid. We'll use them all twice except the ones on the ends. That's something that we'll come back and that will be useful for us later on. Okay, so we got that. Next trapezoid would be F of 0, 1/2, F of 0 plus F of 1, and then plus 1/2 F of 1 plus F of 2. A lot of work. Okay, now this is going to end up being 0 also. This was -2, so that gave me -8. This was -1, that'd be -9 times 1/2, that'd be -9/2. Plus, this one would be -1 plus 0 times 1/2, that's -1/2. And then the next one would be +1/2. And the last one would be 9/2, and so we know that's going to add up to 0. Okay. Made. Left, right, midpoint, trapezoid. You're going to have one problem just like that, where that's what you work out. Okay, it's not symmetrical though, and so you'll get a little more interesting answers. All right, now, let's just keep right on plugging along here. Well, so I guess what I want to do, so I want to give you a definition here. We're going to talk about that. And then we're going to go right into the homework. I'm going to work number 1 with you, and then you can just go from there. Okay? So what we have done here is we have done something called Riemann sums. These are called Riemann sums. Now, technically, let me back up a minute. Trapezoids are not. Riemann sums. So in your notes, let's do this. Let's just write down this definition, and I will go through it here with you. All right, a Riemann sum. Now this is actually named after a person, George Bernard, German. German mathematician, Riemann. So Riemann sum. So what we were doing there is basically what you want to write down for Riemann sum. It's adding rectangle letters. That's what it is. That's what a Riemann sum is. Adding rectangle letters. So trapezoid doesn't count. Trapezoid is not a Riemann sum. It's still a way of finding area. It's still a way of approximating area, but it is not a Riemann sum. Riemann, think R for Riemann, R for rectangle. Riemann sum is adding rectangle area. Now, this is going to get really technical, but this is like what we were talking about earlier we did with the f of x plus a plus h minus f of x all over h, blah, blah, blah. That's what we're working on right now, okay? That for areas. So, here's how it starts. Let the interval AB be partitioned into n subintervals by n plus 1 points. So we just had the situation earlier where you had 4 subintervals divided by 5 points. That's what I mean. Okay? So we're going to divide the interval AB into n subintervals. Now this next part there is notation. Just like we used a and a plus h, right, in our derivative thing. A and B are our left and right edges. But and we want to divide that into n subintervals, we need n plus 1 points, right? So if we have 10 subintervals, we want the last one to be x sub 10, so we have to start with x sub 0. So A, our left edge, we're going to call x sub 0, and then x sub 1, x sub 2, x sub 3, x sub 4, like what we just had where we had the 5 points. We'd have called the left edge x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4 would have been the last one. So x sub 4 is actually the 5th point. Yes, I did that wrong. Yeah, I noticed that in the other class, and then I forgot to fix it. This would be minus 1 right here. This should be x sub n minus 1 right there. Okay? So x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, x sub n minus 1, and finally x sub n is the last one, which is the b. Okay, so that's what that means. So it's just explaining our notation. All right. Let delta x equal, or delta x sub I equal the width of the ith subinterval. Well, I'll explain that. Now, we were talking a minute ago about delta x. We didn't have this sub I. Well, that was because our widths were all, on those examples we just did, what? The delta x was 1. Every subinterval was a width of 1. And 90% of the time, maybe 95% of the time, we will divide our interval into equal subintervals. But they wouldn't have to be. They wouldn't have to be. We wouldn't have to have every subinterval be the same. They can all be different. So, you could have delta x1 be the first subinterval, delta x2 be the second, delta x3, delta x4. That's why this is here. It could be that way. We hardly ever will do it that way. Right? About the only time would be, well, I'll show you an example in that packet I gave you yesterday, as a matter of fact. But hardly ever will that come up. Anyway, delta x is basically the width. That's what you want to get from that. Within each subinterval, let C sub I be the sampling point. So that's, the sampling point was like our left edge, or our right edge, or our midpoint, and we're not doing trapezoids now, right? We're just talking about right thing. But it wouldn't have to be one of those either. We could pick a point just like a fourth of the way in, or 2/3 of the way in to our subinterval, right? And that could be our height. We don't have to pick the left edge, we don't have to pick the right edge, we don't have to pick the midpoint. It's just those are convenient, and those are the ones we work with, again, 90% of the time, or maybe more. But we're going to let C be the sampling point in the subinterval. Then this sum right here, so look what this is. This is what we were just talking about. I'll call this S for sum, sub n, meaning how many terms we have. F of C1 times delta x1. So look what that is. That's height times width, plus height times width, plus plus height times width. Those are rectangle areas, right? Height times width, height times width, height times width. We add those up. This is called a Riemann. This sum is called a Riemann sum for that function on the interval AB. So, that thing we were just writing out, that L4, R4, M4 that we wrote out, those are called Riemann sum. Finding rectangle areas. Okay? Now I'm going to talk briefly about, show you an example about how they don't have to all be the same width. I'll show you another example from that packet yesterday of just what a question looks like. It talks about Riemann sums. That's a little ahead of where we're at right now. Okay, so I'll come back to this if you don't have it all. If you don't have it all written, if you need to, just let me know. But here is picture. This is actually in your book. This would be a Riemann sum. 1, 2, 3, 4, 5, 6 rectangles. They don't have the same width. And they're not all at the same place. In other words, this sampling point, this function height it looks like it's a little left of the midpoint. And same with this point. But this one's at the right endpoint. This one looks like it's at the right endpoint. This one looks like it's a little past the midpoint. Right? But it's still a Riemann sum. It's a function height times a width. Function height times a width. Function height times a width. Right? It's a Riemann sum. It's just, but why would you want to do that? That just complicates things, right? So normally we would never do this, but it still qualifies as a Riemann sum. Okay, the other thing I wanted to show you is in that packet I gave you yesterday. You don't have to look at this, but this was number 1 that we did in class. Remember the temperature? We skipped part C, right? Well, first of all, look at the width of your subintervals. Are they equal? Do you have a choice? Can you make them equal? No, you have no choice. This is the only data you have. So you have no choice. You have to work with unequal subintervals, okay, when you have a table of values. Look at part C. Says, whoa, the average temperature of the water is this. That was the average value function formula, by the way. Use a left Riemann sum with 4 subintervals to approximate this integral, right? So that's what we're going to do. That's what we'll do. Here's an integral, just like the ones we just did for number 17. Use a left Riemann sum. So they want 4 left rectangles is what they would want there. We'll come back and do that one later after we practice a little more. All right, so let's dive into the homework. Here is problem number 1. So I'll let you get organized with your notebooks and everything. Homework is section 5.6. I think it starts on page 354. I'm going to shorten it a little bit from what's on the assignment sheet. So it's 1 through 6. Number 7, there I go again. This is 5.6. 1 through 6. Number 7. Number 10. And number 16. Okay, so 16 is the one we talked about where you got 4 parts to it. You're going to have 4 pictures for that one. 7 and 10, you write out the sum. I think on 7 it says, estimate the value of this integral using a right sum with 3 subintervals. It doesn't say draw a sketch, so you don't have to draw. If it doesn't say draw, you don't have to draw. So 7 and 10, you won't have to draw, but you'll just write out the sum. 16, you'll have 4 drawings and 4 sums written out, just like we did 17. And on 1 through 6, on each one of those, you'll have 1 drawing and 1 sum written out. So we'll do number 1 together, and then you can just keep working. Okay? You've been nervous. All right, so you're going to draw this picture like 6 times. Okay, once each for problem 1, 2, 3, 4, 5, and 6. Okay, so sketch it kind of the best you can. Maybe label these points. Right, that's what I did. I just went and found the nice, neat points, labeled those, and drew myself that little sketch there. Okay, make it fairly good size. I mean, I think in your homework, right? So you're not drawing these tiny little squares, little rectangles, because on the quiz you're going to want to draw them, fairly neatly. All right, so for number 1, now I think they have part A and B switched around. It says part A says estimate the value of the integral of -5 to 5. So the integral from -5 to 5 of g of x dx. And this is the g function here. Estimate this using left sum with 5 subintervals. But then in part B, they said to draw the sketch. Well, I think I'm going to draw the sketch first. I think it's easier to draw the sketch first. Okay? So what's the first thing we should do? In starting to draw these sketches? What do you think? I agree. I think figure out the width. Now, in the other class, somebody said, well, go to -5, go to the left edge, because we're doing 5 left rectangles, what we're doing. So somebody in the other class said, well, go to -5 and put your dots, put your dots. And then they're like, oh. And I'm like, well, where do I put my second dot? Oh, you got to find the width, right? So I agree. Finding the delta x, I think, is the key first step in any of these Riemann sum kind of problems. So delta x would be the total width, which is 10, divided by 5 subintervals, so it's how much? 2. 10 divided by 2. So I'm going to put my dots 2 apart. Right? So there's my 5 subintervals in the blue. In between the blue dots. Those are my 5 subintervals. My subintervals are 2 wide. So now I'm going to go and I'm going to do left rectangle. So just like we did for problem 17, I'm going to go to my left edge, down to the curve. I'm going to go over 2. And I'm going to go back. And there's my first left rectangle. I'm going to go to my left edge. I'm going to go up to the curve. I'm going to go over 2. And there's my next left rectangle. Go to my left edge, up to the curve, over 2. What happens on the fourth one? It's just a flat line. It's just a 0 height rectangle. You can kind of scribble it in there to kind of emphasize that, but there it is. I mean, you don't have to draw anything either if you don't. You can leave it blank. And then the last one, left edge down to the curve, go over 2, and there is that one. So that's the first part. That's actually part B, okay? And then part A is draw or evaluate, or calculate the L5. So let's use our function notation. This is G we're doing this time. So this is G of -5 times 2 plus G of -3 times 2. In the early stages, it's easier if you have the picture because you can just look, but you'll soon learn that, oh, since the width is 2, these numbers in here, the input numbers have to go up by 2 because I'm moving over 2 every time. So this one's going to be G of -1. So that's what you're going to get a practice on 7 and on 10. You don't have to draw the picture. Oh, whoops, that's a 2. You don't have to draw the picture on 7 and 2 because it didn't tell you to. You should be able to write this out without the picture. You just know the left edge is, the left rectangles are going to start at the far left edge, which is -5. And since the width is 2, I'll go over to -3, to -1, to 1, to 3. And since they're lefts, I won't go all the way to the far right one. So I'll stop. And plus you'll know because you only should have 5 rectangles here. Height times width, height times width, height times width, height times width, height times width. Okay? All right, and now plug the actual numbers in. You read them off the graph. So G of -5, that's what? -2 times 2, that's -4. G of -3, that would be up here at 2 times 2, that's +4. G of -1, that is 3 times 2 is 6. G of 1 is 0. And the last rectangle, G of 3, is -1 times 2 is -2. We add those all up, we get 4. And there is our problem number 1. Okay? So, go ahead and keep working. Our goal after today, because we want to get in tomorrow into then working with it, feeling comfortable with this notation. So our goal today is to be able to draw rectangles. And you might have some trapezoids. I'm trying to think if 10 is a trapezoid. There's 4 trapezoids. 4 is trapezoid. So you're going to get draw some of all of them. Be able to draw them. Be able to write them out. These areas, right? And then we'll move on into the kind of what we're going to do with that from there. All right.
Yeah.
Yep, done with hats.